Hi, my name is Paul Cupit, and this is our project report presentation on waterflood optimization. We are Group 10, and our members are Luke Bigham, Conner Ardoin, Paul Cupit, Chelsea LaRicci, and Jeff Burton. As project manager, I will be introducing you to the certain aspects that this presentation will cover. As you can see in the figure shown, certain project milestones are highlighted. These include approval on testing apparatus or simulator, determining possible oil field to study, research, obtaining field data through testing, and the start of our simulating our data. Today we will discuss the progress our group has made so far in accomplishing these goals. To start, I have put our milestones in an Excel spreadsheet to design a Gantt chart. It incorporates all the main project items to be accomplished by the end of the semester. The project charter is fully completed along with our progress presentation. As you can see, we are still in the early stages of research. At this point in our project, we have not started simulating or testing, but I will address this later. Our meeting minutes are also up to date. This next slide is a calendar representation of the previous Excel file. Essentially, it is a Gantt chart to show the progress we made so far in relation to due dates and a timeline. As previously mentioned, we have not started simulating or testing data. However, we are making progress towards starting this goal. I have talked with Dr. Rao to get advice on how to test waterflood optimization. He recommended against lab testing and suggested simulation, which LSU provides for our use in the Petty Computer Lab. I have emailed Watik, who is a grad student and proficient with the simulator, to hopefully get some guidance on how to use the simulator. I also have contacted a few graduate students to see if they were doing research on water flooding, and maybe they can aid or give us pointers on how to approach our project. In order to do simulations or lab tests, we must first obtain field data from either a company, our sponsor, or the internet. We are currently in contact with multiple people about obtaining field data to use as a reference, and we are currently waiting to hear back from them. Our next presenter will be Chelsea, who will be presenting the progress our group has made on research.
Hi, I'm Chelsea LaRicci, and next we will be talking about the progress our group has made on our various research topics, which are water injection rates, sweep efficiency, injection well patterns, and water additives. I am currently researching the water injection rates of a water flood. Water injection rates are directly related to production rates and plays an important factor in the overall volumetric sweep efficiency. The definition of critical water injection rate is the maximum injection rate at which the capillary imbibition is not effective. While higher injection rates result in faster recovery and have the ability to suppress gravity-dominated underruns, it also results in high pressure. With the increase in pressure, the chances of fracturing the reservoir increase as well. While slower injection rates promote capillary cross-flow, which can be beneficial for increasing sweep in lower permeability layers. Therefore, the optimal injection rate will depend on the particular reservoir in question. With further research and possible laboratory testing, we plan to find the optimal injection rate for our reservoir via simulation or through decline curve analysis. We are currently contacting personnel to get access to the Petroleum Fluids Lab at LSU to test core samples in order to obtain properties about the reservoir we are focusing on. Next presenter will be Luke, discussing his progress on sweep efficiency research.
Hi, my name is Luke Bigham. Since the project charter, I've been assigned the task of studying sweep efficiency and its relation to water flooding. Sweep efficiency is the volume of the reservoir pore space contacted by the injection fluid. Basically, it's the amount of pore space in the reservoir that the injected water travels through. The overall sweep is a product of the aerial and vertical sweep efficiencies. Essentially, these are horizontal and vertical components of the overall sweep. The sweep efficiency is also associated with the mobility of the fluid in the reservoir. The mobility is related to a fluid's resistance to flow, viscosity, at a given saturation of that fluid in this certain reservoir. The higher the mobility, the easier the fluid will flow out of the formation. Gases have low viscosities, so gas mobility ratios are typically high. Oil mobility ratios are not, and so those are the ones that typically need to be increased. Although not always the most cost-effective, an increase in injection flow rates will increase sweep efficiency. Our purpose would be to find the flow rate that gives us the best production at the lowest operating costs while still maintaining safe and feasible rates. Other enhanced oil recovery methods can be applied to improve sweep efficiency. An example of this would be the application of conformance techniques, which would entail the use of gels, foams, polymers, and resins to enlarge the sweep and or reduce the competing gas and water production. My colleague Jeff will now speak on the impact that injection well patterns have on water flooding.
Hi, my name is Jeff Burton, and I am a member of Petroflood Solutions and the senior class of LSU's Petroleum Engineering Department. In this early stage of my group's project, my part was to research the injection and production well patterns used in the enhanced oil recovery method of water flooding. The selection of the most efficient injection and production well pattern is one of the most important steps in the design process of a profitable water flooding application. As you can see on this slide, there are many different patterns to select from. The patterns shown are an ideal setup and are not exact representations of a real-world water flooding technique. The most important factor to take into account during this pattern selection is to increase the profit made from the production well, often by turning old production wells into injection wells, with a higher number of injection wells in comparison to production wells. The patterns shown are made with the idea that the producer will use the existing wells in the region and adapt them accordingly. As stated before, the most important factor in selecting the proper pattern for injection and production wells is to determine the most profitable pattern available. The items listed here are the most important determinant factors in well pattern selection. As mentioned before, the real-world pattern is not exactly the same as the ideal pattern shown previously. This figure shows what an adaptation of a 5-point well pattern looks like when placed into a real oil field. Going forward, I plan to further analyze the finer details of well pattern selection. I plan on analyzing field studies with analyses of the selection of injection well patterns and determine how to apply this information to our project going further, especially for the simulation step of our project. Coming up next in the presentation is Conner Ardoin talking about water additives.
Hi, my name is Conner Ardoin, and since we last spoke, I have been researching the use of water additives to enhance water flooding. Polymer flooding is a well-known enhanced oil recovery technique that is implemented worldwide for medium and light oil reservoirs. The use of polymers in the floodwater improves vertical sweep efficiency of water flooding through mobility control. It is beneficial because it lowers overall costs, decreases deployment time, and extends water flood applicability. One problem experienced in water flooding is that the low viscosity of water has trouble diverting medium to light oil through tight pore spaces because water will flow in the path of least resistance and typically bypass large quantities of oil. Viscosifying the flood water with polymers solves this problem and also reduces detrimental fingering effects. I plan on using a rotational viscometer to measure the viscosity of brine solution versus the brine solution with polymer additives, as well as the optimum polymer concentration. With polymer flooding, production is increased up to 3 times its original rate, has recovery factors from 5 to 15%, and decreases water cut up to 50%. Adding polymers to the floodwater extends the life of the reservoir while keeping operational costs close to that of water flooding alone. In the upcoming weeks, my plan is to look into the economics of polymer flooding by researching prices of different polymers. I also plan on analyzing the effective change in the viscosity of the flowing fluids from the derivation of the reduced Buckley-Leverett fractional flow equation using the following assumptions. Gravity and capillary effects are negligible, pressures in the oil and water phases are the same, and viscosity ratio is some fixed value.
In conclusion, we are on track with our project thus far and haven't fallen behind any major project milestone deadlines. We are planning to start simulating within a few weeks, and by the end of the semester, we should have a few good base simulations to build off of in the spring.